Moving on to the next topic, that is three-phase circuit with balanced and unbalanced load. Okay, this is the module first unit. Just to analyze what is this balanced and unbalanced load, what are these three systems, how it is done, how the angles of voltages and current are kept at 120 degrees at a difference at an angle of 120 degree. So in what is that, we'll first see the definition of balanced load. Okay, in balanced load, a three-phase system, or in balanced a three-phase, all the three system voltages are, that is important, all the three system voltages are equal and separated each other by 120 degree. Okay, the system voltages are equal and they are separated by 120 degree. That is called as balanced three-phase system. Here this is the figure we draw. There are three ways of representing it. We can represent it as ER, EY and EB. Okay, this is red, yellow and blue. That is one way of representing, or we can represent it as EA, EB or EC. Okay, three voltages, they have just represented the with the lines and it is separated by 120 degree. The angle of separation between all the three is 120. And the equation you Em sin omega t. If you take ER as Em sin omega t, Em is the voltage. Okay, this is small er. So Ey is equal to Em sin of, it is difference, the difference between this both Er and Ey is this 120 degree. Okay, this is, since it is coming downwards, we write it as negative, minus 120. And between this ER and EB, it is Em sin of omega t minus 240 degree. You can write it as minus 240 or you can write it as plus 120. Okay, it can be plus 120 if you go from here. If you go in the clockwise direction, of voltages EY and EB. And the angle is important. First one is Em sin omega t. Second one is Em sin omega t minus 120 degree. Third one is Em sin omega t minus 240 degree. When all the three voltages have same voltages and magnitude but differ in phase by 120 degree with respect to one another, it is called as three-phase supply system. Okay, if one of the above condition is not satisfied, see what we are telling, all the three voltages have same voltages and magnitude and differ by 120 degree with respect to one another. So if voltages are not same, or if the angle is not 120 degree, if any one of the condition is not satisfied, then we call it as unbalanced. Okay, this both the conditions should be satisfied for balanced. If any one is not satisfied, then we call it as unbalanced. So that is one definition. Next, there are two types of three-phase connections. Okay, we have this star and delta. We had seen in the first module the star connection and delta connection. So here also in three-phase we have two types. One is star connection and the other is the delta connection. So we'll go on with one by one now. What we'll see first, what is this star connection? In star connection, I'll just star connection, the network is shown here. Fine, we have three networks here, EAN, EBN, ECN. Okay, there is a neutral point here. Okay, three branches are connected to this neutral point. Fine, and all the other end, one end is connected to the neutral point and the other end is brought outside. Here we show three terminal points. From one terminal point, the current IA. Then the second, the current IB, and the third is the current IC. Okay, and the difference in voltage EAB, okay, EBC and EAC. This is how the star connection of a three-phase system. And the voltages here in the branches, it is shown as EAN, between A and the neutral point. Between B and neutral point, it is EBN and it is ECN. So one neutral point will be there, one terminal of the branch will be connected to the neutral point and the other terminal or the other side will be used to send the IA current where the source or load will be connected. So here EAN, EBN and ECN, okay, this one EAN, EBN and ECN are called phase voltages. Okay, this branch voltages, they are called as phase voltages, and this EAB, EAC, EBC, this the voltages which we have written here are called line voltages. Fine. Next, the formula for finding out the line voltage is root 3 phase voltage. Okay, line voltage VL is equal to root 3 into phase voltage, and in star connection one important concept is line current is equal to the phase current. Here the line current and phase current are both equal, only the line voltage and phase voltage will differ. Okay, when solving the problem you have to remember. Next, this is the delta connection. Here there is no neutral point for delta connection. The three terminals are IA, IB and IC, and this phase voltages are IAB, IBC and ICA. So the formula here, it is just opposite of star. So we have here line voltage is the same as phase voltage. Okay, in star connection line currents and phase currents are same, and in delta line voltage and phase voltage are same, and the line current is equal to root 3 phase current. So these are the two formulas, and the formula for active power. See, this all are I'm putting for balanced. The active power in balanced three-phase system is, okay, V is equal to root 3 VL IL cos pi. Okay, cos pi watt. So to find out this cos pi only, we have to draw the phasor diagram. Okay, that's to find out the active power. Next, the total apparent power for balanced three-phase system is, for apparent power we'll go with S is equal to root 3 VL IL V amps. Volt ampere is the unit. Okay, for active power it is watt. For total apparent power it is volt ampere. And one more power we have, that is total reactive power. The total reactive power Q is root 3 VL IL sin pi, and the unit is VAR. It is volt ampere reactive. For total reactive power we go with sin pi, and for total active power we go with cos pi. These three formulas with line current and phase current you have to remember. Once again I'll tell, for the line current is in star connection the line current and phase current are same. In delta connection the line voltage and phase voltage are same. Okay. Next we'll see what is this unbalanced star connection. See, as shown in the figure you can see that in unbalanced all the loads are differing, they are not same. It is 5 at an angle 30, this 15 at an angle 0, this 10 at an angle minus 60. Everything is changed here, and it is IL1, IL2, IL3 are the line currents. Okay, RYB are the terminals, and we have a neutral point. Just to show that you have to write phases here. ZPH1, ZPH3 and ZPH2 all differ. In unbalanced delta connection, okay, this is star connection. In unbalanced delta connection, same thing. We show 7 at an angle 0, 8 at an angle 45 and 15 at an angle 30. This is the delta connection where all the phase voltages are differing. Okay. In general, there are three types of unbalanced load connected. Okay, we'll see three types here. First one is unbalanced 3-wire star connected load. First one. This system, the neutral point of the supply system. Okay, supply system and load. Two things they will be considering here. In this system, the neutral point of the supply system is called as O. Is not as the potential of the load neutral N. Okay. Supply system neutral point is O, and the load point neutral point is N. Okay, two different symbols are used, O and N. The displacement of the voltage between the neutral points, that is between the supply and load, is called shifted neutral voltages and is obtained by, okay, the shifted neutral voltage is obtained by VNO, that is the neutral point of the supply and neutral point of the load is equal to, this is the formula of Millman's theorem. The same formula is used here, VAO between A, B and C and their admittance YA, YB, YC divided by YA plus YB plus YC. Here this all this whatever VAO, VBO, VCO is nothing but the phase voltages, and all others are the reciprocal of the load impedances. That is ZA, ZB, ZC, they'll give, it will be YA, YB and YC. That is the first point. Next, in figure 2 shows unbalanced delta connected load. Okay, this figure 2 was, I'll show you the figure at the end. Next, the unbalanced 4-wire star connected load. Okay, this is the unbalanced 4-wire. In this, the star connection load and the 4th wire is used to connect the neutral of the load to the neutral of the supply system. So two things, one is the load and one is the supply system. Here extra wire is used to connect. This is the supply and this is the load. Okay, this extra one, this is used to connect between the neutral of the supply and neutral of the load. And one more thing, the neutral wire with zero impedance has the current IN is equal to IR plus all the three currents, that is from the R, Y and B terminal are added. Neutral wire with impedance Zn, that is given with the same formula. Here with the neutral formula will be used, that is VNO is equal to ER/R plus EB/YB plus EY/Y and divided by all the impedances plus neutral impedance. So